Okay, here's some more simple harmonic motion. So if a body moves with simple harmonic motion, let's define in words. Oh, I've just chopped off the end there. That's going to be simple harmonic motion. So define that in words. Let's start with the formula. So for simple harmonic, we know we want this. So let's turn that into words. So we've got acceleration. I'm doing this in note form, so I haven't got much space. Acceleration is proportional to displacement. Displacement, you have to say displacement from where, so displacement from an equilibrium position. And because it's more than just that, we've got this minus sign sitting in here, and acceleration acts towards the equilibrium position. So provided you've got those two bits, then you're going to be fine. Right, now they're getting this onto an actual bit of calculation and a real world scenario. We've got a horizontal metal plate connected to a vibration generator oscillating vertically, right? So it's bouncing it up and down with SHM of period 0.08, amplitude 1.2 millimeters. Okay, calculate the maximum speed of the plate. Okay, well, let's pull out this t equals 0.08 seconds. That's useful because that's going to give us the frequency, which is 1 over that. So that's going to be, rather than 8 over 100, it'll be 100 over 8. So that's 12.5 hertz. That is our frequency. The maximum speed, well, actually, while we're at it on all of these, we might as well, oh no, let's just stick with what they're going for. So Vmax, we know, is omega A. I was going to say, should we just work out all of these things? But I've started reading the question now, so I might as well just do things in order. And omega is 2 pi f. The A was, what was A? 0.0012. That's millimeters, isn't it? Yeah, because centimeters is 0 something. Yeah, so that's millimeters, 1.2 millimeters. That's our A, multiplied by 2 times pi times 12.5 is our F. Okay, I mean, we could have just stuck with T, 2 pi over T, but you know. So typing all of that into the calculator, our 25 pi times that, we get 9.4 times 10 to the minus 2 meters per second. That's our maximum speed. So next bit, frequency of the vibrating plate is kept constant. Its amplitude is slowly increased from 0. Grains of sand start to lose contact with the plate when its amplitude is A0. State and explain the necessary conditions of the grains of sand, when they first lose contact with a plate. Okay, so when are we first going to get the grains losing contact with the plate? So it's going to happen when, so we need A max, which is at the high point, A max at highest point, because when you get to the highest point, when the plate is at the top, it's going to turn around, it's going to be going back the other way. Excuse me. And we're going to have a maximum acceleration going downwards. So A max at the highest point, if that is greater than the acceleration due to gravity, then the plate will be moving downwards at A max, and the grains of sand will be moving downwards with an acceleration of G. So they're both stationary. So we want to put something in here. So we can say at highest point, we've got the plate and grains are stationary. Then plate accelerates down at A max, and the grains accelerate down, and grains accelerate down at G. So if if A max greater than G, then grains off plate. And now they're asking us to work out what that is going to be. Okay, so we need A max is equal to omega squared A. So we need, and that has to be greater than G. So we need A to be greater than G over omega squared. So that's G over 4 pi squared. Oh yeah, it was 12.5, wasn't it? Times 12.5 squared. So taking 9.81 for G, we're going to get that A has to be greater than, how many zeros again have we got? 1.6 millimeters, give or take. So yeah, if A is greater than that, then everything is fine. Right, I've taken up the whole screen now, so let's see what we need for C. The casing of a poorly designed washing machine vibrates violently when the drum rotates during the spin cycle. Yep, sounds like my washing machine. When that shows how the amplitude of the casing varies with frequency. Okay, state the name of this effect and describe the conditions under which it occurs. Right, so we want to say, I just want us to state it. So we've got resonance, and this is when the driving frequency, i.e. the frequency of the drum, so that's what's driving the casing, equals the natural frequency of the casing. So it's worth saying, as they always want in these questions, they want to say, want you to say what's doing the driving, in this case the drum, and what's being driven, in this case the casing, because it's the casing that is vibrating. It's the casing that resonates, and that resonance is being caused by the rotation of the drum. So we need to get that the right way round and actually mention both of these things. Right, the design of the washing machine is improved to reduce the effect by adding a damping mechanism to the inside of the machine. Sketch on the graph, new graph of amplitude against frequency of rotation. Okay, so we want everything to be lower, because if it's damped, it's going to bring the amplitude down. And we also need to remember that the natural frequency must be either the same or lower than the previous natural frequency. So provided we've got something that's below this line all the way along, and this peak, the green peak, is to the left of the original peak, then we're fine. So yeah, we just sketched that on, and that's all they've asked for, isn't it? There's no explanation or anything. Yeah, sketch the graph. So there'd be the two things that they're looking for: everything being lower and where the peak is. So yeah, there you go. That's got some tough bits in it, really. I mean, this part here, this second part of B, isn't trivial. You know, you've got some stuff you need to think through. So yeah, another nice question.